Namaskar, I am Dan Gaude, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the kinematics of the rigid body from classical mechanics. Last topic example here. Explain how the generalized coordinate of a rigid body with n particle reduced to 6 for its description. Generalized coordinate of rigid body. A system of n particle free from constraint can have 3n degrees of freedom and hence 3n generalized coordinate, but the constraint involved in rigid body with n particle are holonomic and scalonomic and are given by Rij is equal to Rij bar is equal to Aij, I is not equal to j 1 2 3 dot capital M, where Rij bar denote the distance between the ith and jth particle and Aij are constant. Equation Rij bar is equal to Aij is symmetric in I and j, and I is not equal to j as the distance of the ith from itself is 0. Therefore, the possible number of constraints is nc2 is equal to n multiply n minus 1 divided by 2. We notice that for n greater than 7, n into n minus 1 divided by 2 greater than 3n. Therefore, the actual number of degrees of freedom cannot be obtained simply by subtracting the number of constraints from 3n. This is simply because all constraints in equation 1 are not independent. To show that the relation how the generalized coordinate of a rigid body with n particle reduces to 6 for its description. Let a rigid body be regarded as a system of at least 3 non-collinear particles whose position relative to one another remains fixed. Thus, a system of 3 particles free from constraint has 9 degrees of freedom, but there involve 3 constraints. Hence, the number of generalized coordinates reduces to 6. Thus, the total number of degrees of freedom for 3 non-collinear particles A, B and C of a rigid body is equal to 6. This is because each particle has 3 particles of the freedom and less 3 equation of constraint. The position of each further class particle, say P, requires 3 more coordinates for its description, but there will be 3 equations for constraint for this particle because the distance of P from A, B, C is fixed. Thus, 3 coordinates of P and less 3 equation of constraint for P gives 0 degrees of freedom. Thus, any other particle apart from A, B, C taken to specify the configuration of the rigid body will not add any degree of freedom. Once the position of 3 of the particle of the rigid body are determined, the constant picks up the position of all remaining particles. Thus, the configuration of the rigid body would be completely specified by only three particles and by 6 degrees of freedom, no matter how many particles it may contain. Example second, describe the motion of the rigid body. A rigid body can have two types of motions. First, a translational motion. Second, and a rotational motion. Thus, rigid body in motion can be completely specified if its position and orientation are known. However, if one of the points of a rigid body is fixed, the translation motion of the body is absent and the body rotates about any line through the fixed point. Again, if we fix up a second point, then the motions of the body is restricted to rotate about the line joining the two fixed points. The position of the body is fixed and there is no motions of any kind. The coordinates of the third point alone will be able to locate the positions of the rigid body completely in space. It follows that the position of the rigid body is determined by any three non-collinear points of it, that is by 6 degrees of freedom. Of the 6 generalized coordinates, 3 coordinates are used to describe translational motion and other 3 coordinates are used to describe rotational motion. Since a rigid body with one point fixed has no translational motion and hence it has 3 degrees of freedom and 3 generalized coordinates which are used to describe the rotational motion. Next, orthogonal transformation. Define orthogonal transformation. Show that the finite rotations of a rigid body about a fixed point of the body is not commutative. Solution. Consider x1, x2, x3 and x1 dash, x2 dash, x3 dash with two coordinate system. The general linear transformations between these two coordinates system is defined by as the following sets of equations. x1 dash is equal to a11 x1 plus a12 x2 plus a13 x3. x2 dash is equal to a21 x1 plus a22 x2 plus a23 x3, and where a11 a12 dot dot a33 are constant. These three equations can be combined into a single equation as xi dash is equal to summation of aij xj, j is equal to 1 to 3, where A is equal to Aij is called the matrix of the transformations. Let a vector r bar is equal to x1i plus x2j plus x3k. Define x1 x2 x3 coordinate system be transformed to x1 dash x2 dash x3 dash coordinate system in the form r bar is equal to xi dash I plus x2 dash j plus x3 dash k. Since the magnitude of the vector must be the same in both the coordinate system, we must have therefore summation of xi dash square is equal to summation of xi square. Using equation 2 in equation 3, we get summation of aij xj is equal to aij xk is equal to xi square, and this is called delta symbol.